And I believe Sandra's talk today on optimal collusion-free teaching is also in that same general area. So Sandra, welcome. Please go ahead.
Thank you so much. Thank you for the kind introduction and also for the invitation to speak here today. I'm really hyped about this. So as Sanjit said, I'm going to talk about machine teaching. So my point of view is a little bit different because I come from a different area, but I already see so many aspects of where we're thinking in very similar ways and where I think there could be synergies. So what I'm talking about today is just a very, very condensed summary of a number of papers that I published with a number of co-authors listed here on that slide whom I'd really like to acknowledge. And basically, what it's all about is the aspect of machine teaching, where from a machine learning point of view, we look at tailoring learning algorithms to the properties of the source that provides training data, rather than just assuming I've got randomly chosen data. I want to find out, if I can model the source that provides the data in a better way, then perhaps I could be much more efficient in learning. And I think that Sujmit's talk already showed that in the formal verification and program synthesis community, you're actually doing something similar. You're tailoring the algorithms to properties of oracles. And I think Sujmit phrased it this way: we design learner and oracle together. So that's really very much the kind of way of thinking that I like. And that's why I think our research kind of connects. So in my formal learning models that I'll be talking about today, I will always be assuming there is some instance space that could be any set X, and a concept is just a subset of that instance space. A concept class is a class of concepts. The learner will be presented with labeled examples for concepts. That means just a pair where X is an element of the instance space and L is a label, either 1 or 0, depending on whether or not X belongs to the concept. In this simple example here, X is the Euclidean space and the concept class would be all orthogonal rectangles. And this could be one target concept with a bunch of examples that the learner sees. In computational learning theory, we have lots and lots of formal learning models and compare them to each other. Some of them assume that the source of information that produces the examples is some random variable that somehow follows some real world distribution. One model of random examples is the PAC model, is very popular. And the learner then receives these examples for the target concept and produces a hypothesis. Both the information source and the learner do know the whole class of concepts, but of course the learner does not know which one is the target concept. That's what it's supposed to be figuring out. There are also models where the learner chooses which examples it will be presented with. So it picks the X's and it sees the correct labels for them. This is active learning. Here, the information source is not a random thing, but it's an oracle. And then the models that I'll be looking at is a model of a teacher that is benevolent and chooses the examples in some helpful way. And in particular, I will look at only exact learning. So we're not approximating the target concept. We want to identify it exactly. Why would you ever consider something like machine teaching? So there are relations, for one thing, to several other research areas. As the reason I'm here is because we all believe there's relations to model checking, program synthesis. There are relations to robot-robot interaction, programming by demonstration or programming by example are keywords where a teacher plays a role. And also on the interface between computer science and psychology, people study machine teaching. I know of some people who work in both fields and use concepts from one in the connection of in the context of the other field. So that's quite interesting too. Also within computational learning theory, it relates to other topics such as sample compression, active learning. Whenever we study sample complexity, notions of teaching do come up. And at the end of the day, we always ask ourselves how small a training data set is sufficient for learning. So how small can the teacher make the number of examples so that the learner can still identify the target concept correctly? The classical notion of teaching goes back to the early 90s. Several research groups have worked on it independently. That's the teaching dimension notion. Here, to teach a concept really means to provide a set of labeled examples, which we call a teaching set, T of C. All these examples are labeled correctly for C, so there's no noise. And that teaching set T of C has to disagree with all the other concepts in the class, so that it really uniquely identifies the target concept. There's a corresponding complexity parameter called the teaching dimension. The teaching dimension of a concept C with respect to the class C is just simply the smallest possible size of such teaching set. And the teaching dimension of the class is just the worst case teaching dimension taken over all the concepts. For example, if the concepts are circles in the Euclidean space with positive radius, so just the circular lines, not the interior, then you can teach any concept with 3 examples by just putting them, taking 3 positive examples. So 3 points on the circle, then of course there's only a single unique circle that contains those 3 points. Therefore, the teaching dimension here in that case is 3, because it's also easy to see that less than 3 points won't be sufficient. However, if we now fill these circles, if we make them filled balls with positive radius, then the teaching dimension is infinite if we do really exact learning, not approximating, because obviously, no matter how many positive examples I put into that orange ball, and no matter how many negative ones I put outside the orange ball, you can always squeeze another ball in between that is consistent. So hence, you cannot teach them exactly. Now, to overcome the limitations of that classical teaching model, people have looked at notions of cooperative teaching and learning, where the idea is, in the classical teaching model, the teacher assumes that the learner is stupid in the sense that all it does is produce a concept that is consistent with the examples seen. Now, if the learner instead knows something more about the selection process that the teacher uses, then it can make stronger inferences and therefore learn faster. And that is also supported by psychology. Humans do actually do that. They are sensitive to the way observations are sampled. There's been a number of models in the literature on that use this cooperative idea. Balbach was one of the first introducing such a model, but we also had the recursive teaching model about 10 years ago. These models, they overcome some of the limitations, but they still don't work well for geometric concepts over the real numbers. So when we design a new teaching model, there is one thing that we always have to look at is somehow we can't just design it freely. We have to somehow set constraints, limitations on what's allowed. So in particular, we want to avoid some kind of collusion between the teacher and the learner. And it's not obvious how to model or define what is collusion and what is not. Here's an example. You could ask yourself, why wouldn't I simply teach such a ball with 2 points, namely the center point and the North Pole? That would make a nice teaching set. And then the learner could, knowing my selection process, just figure out what I'm trying to teach. That's fine. But now imagine I've picked these teaching sets, and for this orange ball, I throw in an additional example. I give you more information than the teaching set. I throw in this 3rd point. Now, obviously, the problem is, am I teaching you this orange ball or am I teaching you this red ball? Because with these 3 points, you don't know which one is the center of the target concept. So if you were to use center point and North Pole, we would call that a collusion, because what happens is if you add additional correct examples, you're going to confuse the learner. That's something that we want to disallow. That is a notion introduced by Goldman and Mathias in the 90s, that notion of collusion-free teaching. So here, a teacher-learner pair consists obviously of a teacher. A teacher is a mapping that maps every concept in the class to a set of labeled examples that are labeled correctly with respect to the concept C. The learner is successful only if it decodes the teaching set for C again to C. And that pair is called collusion-free on that concept class if The following holds whenever I add more examples to a teaching set for C and the examples are all consistent with C, then it will not throw the learner off. The learner will still say C. And that is not the only notion of collusion freeness that you could envision, but it's the most often adopted one in the literature, just maybe because it was the first one to be proposed, and it happens to be the case that lots of models do fulfill this notion. For example, the teaching dimension model obviously satisfies this collusion freeness notion. Also, the recursive teaching model that I introduced, or not introduced, but mentioned before, satisfies this notion of collusion freeness. So it seems to intuitively make sense. It seems to be a reasonable requirement. So then you can ask yourself, in particular, because in the literature there have been many models proposed that meet this notion of collusion freeness, what's the best possible you could do for this constraint? What's the best possible teaching rule that you could devise? So that is something that we answered a couple years ago with, actually, it's very, very simple. Both the idea and the proof are just a few lines. A teacher for a concept class C can only then be paired with a learner that is successful and doesn't use, and the two of them don't use collusion, not only if, but if and only if. For any two concepts in the class, we have the following property. The teaching set for C2 is inconsistent with C1, or the teaching set for C1 is inconsistent with C2. So one of them can be consistent with the other as long as it doesn't go both ways. We call this the no clash property. So a teacher with this property is non-clashing. That term was used for a very similar notion in the context of sample compression earlier. And this non-clashing teaching is provably the optimal thing you can do. As long as the teacher satisfies this constraint, it is an optimal teacher under the notion of collusion freeness. And in the example of center point and North Pole, obviously you do have a clash here, because the teaching set for the red ball and the teaching set for the orange ball, they would be consistent in both directions. So that would be a clash, and that wouldn't be allowed. So the no clash teaching dimension is then defined in a very similar way as the teaching dimension before. If we have a teacher mapping T, we say the order of that teacher mapping is just the worst case teaching set size that it produces. And the no clash teaching dimension is the best possible worst case teaching set size for all the non-clashing teachers on a concept class. And therefore, the no clash teaching dimension is exactly the best possible worst case teaching complexity that you can have in Goldman and Mathias's collusion freeness notion. As an example, when you have a finite instance space X, the no clash teaching dimension of the power set over X is half the size of X. I drew just a little example here for 4 instances, 16 concepts. We don't have to go into the details. But there's one thing that bugged us about the no clash teaching dimension when we studied it, and that was a funny ambiguity effect that we observed. So here's a very simple concept class, 4 instances, 4 concepts. The concepts are just intervals of length 2 on this domain. If we look at this concept class here, I've marked in red a potential choice of non-clashing teaching sets. You see, there are 2 concepts that are consistent with this, C1 and C4, with this notion that X1 is 1. There are 2 that are consistent, but C4 has as teaching set X4 is 1, so it's inconsistent with C1, and therefore there is no clash here. So you can choose these teaching sets and not have a clash, but you can also take the second positive example for each concept and also not have a clash. It's the same thing. So this is just a copy again of the same matrix. You see 2 different assignments of teaching sets to concepts are clash-free, and actually the range that the two teachers use is exactly the same. They use exactly the same sets, but encode something different. So they're somehow teacher and learner must disambiguate between that. So is that some additional form of collusion that isn't captured in the notion proposed by Goldman and Matthias? So we therefore defined a different notion, a stricter notion of collusion freeness, which we called unambiguity. A teacher is unambiguous on a concept class C if for every finite subclass and every teacher that is different from T on that finite subclass, the two of them, they cannot have the same range, okay? And this example here shows that there are concept classes for which actually no unambiguous teacher can have order of NCTD. So this is a really stricter notion of collusion freeness than the previous one. And what we found out is that the best possible model under our unambiguity notion is actually one that was published already in the literature by ourselves. So the preference-based teaching dimension model is a model that, that is optimal with respect to this notion of unambiguity. In preference-based teaching, teacher and learner first agree on a preference relation over concepts that induces a partial order over the concept class. Now, to teach a concept in the classical teaching dimension model means to provide a teaching set of labeled examples consistent with the concept in a way that the teaching set disagrees with all the other concepts. Now we're saying the teaching set disagrees with all other concepts that are no less preferred than C under that preference relation. So if concept C prime is less preferred than C, it's fine if it's consistent with the teaching set, because it's less preferred, the teacher will not output, the learner will not output it. Okay, only the higher, the more preferred ones I have to worry about. And again, we can define a preference-based teaching dimension parameter, the size of the smallest teaching set for a concept under a given relation. That would be the preference-based teaching dimension for that concept. For the concept class, again, it's the worst case. And now I can define the preference-based teaching dimension of the concept class to be the smallest possible value that I would get over all allowed preference relations. And what you get then is, for example, with the balls, a very intuitive teaching set. You recall the teaching dimension is infinite, but if we now prefer circles with smaller radius over those with larger radius, then we can teach with only two examples. For the orange ball here, I show it. I pick two positive examples that are diametrically opposed. Obviously, the green ball is consistent, but it's less preferred because it has a larger radius. Obviously, the orange ball is the unique ball, the unique most preferred ball that is consistent with these examples. So that gives us a very simple and intuitive teaching set in that case. And the result that I promised before, if we take any concept class, then the preference-based teaching dimension is really the best possible teaching complexity of any unambiguous teacher for that concept class. Now, one thing that we care about a lot in my community is comparing these teaching complexity notions to one another, and also to complexity parameters that are studied elsewhere. And for example, in the context of learning from randomly chosen examples. The most popular or best known complexity parameter in learning theory is probably the VC dimension, Vapnik-Chervonenkis dimension. It's defined to be the size of the largest finite subset of the instance space, such that the concept class will realize all potential bit patterns over that subset. And it is a parameter that really describes the sample complexity of pack learning, because that sample complexity is linear in the VC dimension. Now, we've been asking ourselves, can we relate the teaching complexity to the complexity of learning from randomly chosen examples? So can we relate our parameters to the VC dimension? It was proven 4 years ago that the preference-based teaching dimension is upper bounded by a function that's quadratic in the VC dimension, but we don't know, can we get linear? We know it's not upper bounded by VC dimension itself, because preference-based teaching dimension can exceed VC dimension by a factor of at least 5/3. I heard just last week, I was at the ALT conference, and somebody told me, oh, we think we have a proof that the PBTD is at most 2 times the VC dimension. That would be nice, but I'm still waiting to see that proof. So that'd be cool. The no-clash teaching dimension is obviously less than or equal than the PBTD, because it is the optimal one that is collusion-free in the Goldman-Mathias sense. And so it's also upper bounded by this quadratic function. But we don't know a single class yet where NCTD exceeds VC dimension. So it could even be that VCD itself is an upper bound. We've also been trying to compare NCTD and PBTD. The largest observed gap we've found so far is examples where PBTD is 4 times NCTD, but we believe that it can actually be arbitrarily large. The problem is it's very hard to set up computer experiments to construct such classes and test them, because of the NCTD being a bit of a beast in that regard, because it's easy, no, not easy to show, but we can show that the NCTD, whether the NCTD is 1 is already NP complete to decide, and also whether NCTD is less than or equal to K for any number K is an NP complete problem. And by contrast, the same questions for PBTD can be decided in polynomial time. So there's actually an interesting link to graph theory. So the proof for this NCTD result is, at least the one we have, is not trivial at all, but it makes a nice connection to the theory of matching. So what you can imagine is just a bipartite graph. The black vertices are concepts. The red vertices are sets of labeled examples. And you draw an edge if a set of labeled examples is consistent with a concept. Now, if these are all sets of size 1, then to have a teacher mapping that maps to that has order 1, you would have to find a matching that assigns a teaching set to each of these vertices here. And in no-clash teaching, that matching cannot have a force cycle of this kind. If I were to assign this set to this concept, this set to this concept, I would have a clash, because these show that I have mutual consistency. So these force cycles are not allowed. And we didn't find any complexity result about that particular matching problem in the literature, but we managed to construct a reduction proof that shows it as NP complete too, and then have actually lots of interesting matching results as well to accompany this. So to conclude, we've seen that no-clash teaching is the optimal collusion-free teaching model in that Goldman-Mathias sense. Preference-based teaching is optimal in terms of unambiguity. There are some interesting relationships between VC dimension and sample complexity, learning from random examples and of learning from teachers on the other side. But there's a bunch of open questions. Can we bound the NCTD above by VC dimension or a function linear in VC dimension? Is the PBTD bounded above by a function linear in the VC dimension? And how large is the gap between those two? And one thing that I'm thinking about a lot is how applications. And I think the preference-based teaching model is maybe more interesting for applications than the NCTD, not just because of the hardness results in NCTD, but I think that this notion of preference relation often is quite intuitive, and humans may use something like a preference relation. I see lots of colleagues trying to impose priors on hypothesis spaces. And I think, wait, that's overkill, right? I don't need a prior. That's like a quantitative notion saying this concept is so and so much more likely than that one. Why not just say, well, it is more probable or more preferred than that one. Maybe that eases things a lot. Maybe there are also some natural or helpful preference relations that could be deployed by oracles and verification and synthesis. So that could be something interesting to discuss with you guys at some point. Yeah, that's my 2 cents on preference-based versus no-clash teaching. And I thank you very much for your attention. And I hope you have some questions.
Thank you, Sandra. Very, very interesting talk. Let me kick off the Q&A with a question of my own. So just to understand the PBTD notions, right? When you say PBTD of a concept class C, you take the worst case over all possible relations, correct?
No, the best relation.
Oh, you take the best relation. Okay, that's what I missed. Okay, so that's why it's so much more compact than the teaching dimension.
Right.
Okay.
Yeah.
I see. And so and the rationale there is that it's because the teacher and the learner are sharing this relation in advance, right?
So if they so unfortunately in the infinite case, they do have to share this in advance. But the nice thing is when the concept class is finite, there is a canonical relation that they can always use, and that is very nice.
Okay.
So in the finite case, they don't have to share any information at all about the relation that they use.
Okay. Okay.
And that makes it, I think, more applicable because I'm bugged by this problem with the infinite concept classes, but I think in many applications you can get away with a finite concept class, and then that problem completely goes away. But that's a very good question. Thank you.
And so we have a couple of questions in the chat and Q&A. So from Marcel Vasquez Shanlade, do we know how stable learning is with preference relations? That is, if I perturb the relation, do things still work out?
Oh, that's a cool question. So I haven't really looked into that, but I can very well imagine that I could concoct an example where things could go really, really wrong if I just make a very little change to the preference relation. I would believe that for certain natural types of classes and relations, it won't hurt too much. And what I would also think is that if one could probably move into a world of approximate learning rather than exact learning, where you could come up with something very much inspired by the preference-based teaching model, where you have more stability or robustness to those changes. But in this very, very exact, strict model that I proposed, I am pretty sure I could come up with something where a little change can have a really bad effect.
Mm-hmm. Okay, great. And there's one more question from Sebastian Junges. For preference-based learning, do you know additional facts about the best relation?
Yeah, as I said, in the finite case, I do. In the finite case, I don't have to think about this at all. In the infinite case, it can be really bad, very hard to come up with this. So sometimes when we want to prove lower bounds on preference-based teaching dimension in the infinite case, it can be very, very tricky because it's so hard to argue that this is the best possible preference relation you can possibly have. In the finite case, it all collapses to something very simple. So basically, you would give the lowest preference to the concept that has the smallest classical teaching dimension. So if there's a concept in the class that can be taught with 2 examples and all the others cost more, then that concept you're actually going to teach with those 2 examples. So you give it low preference because you can have a really cheap teaching set for it. The other concepts that are that need larger teaching sets in the classical model, they have a higher preference, so that you can then give smaller teaching sets for them. And it's very easy to prove that this always works out and always gives you the best possible teaching. It's like you could do a recursive kind of peeling off of the simple concept. So you first, yeah.
Sorry. Is the
you first assign.
There was a follow-up from the same questioner. Is the preference order always a linear order?
No, it doesn't. It doesn't have to be. So in the finite case, of course, you can always, but it doesn't have to be. No, you can have. In the finite case, you can do that, but in general, in the infinite case, so all that's important is that it induces a partial order.
Okay. Okay. Excellent. Thank you so much, Sandra.
No problem. I thank you.
Yeah, and we'll take a very quick 4-minute break now. So get up, stretch your legs, and we'll see you back at 40 past the hour for our next 2 talks.